For this week's project, we're still focusing on MIDI data, and now we're looking at sending MIDI data from a MIDI controller to an LED strip. This is based on the WLED project. The WLED project, it was designed to be a LED strip controller based on the ESP32 microprocessor. So that's the one with the Wi-Fi, the Bluetooth built into it. The project is nice. It's a simple project to install. It's easier than probably installing Arduino on your boards. The project has a website which I'll link in the description, and you go to that website and then you connect your board to your PC like you would do an Arduino, and you download the code onto your board via the browser. I've done that for the Sparkle Motion Mini board from Adafruit. This is a product that Adafruit made specifically for this project, although you probably could run it on another ESP32 with related circuitry to get the LED signal right and the power requirements. Once you've installed WLED on your ESP32, there are a few settings you might need to change. You can set how long the string is in the settings, and you can also set which pin that the LEDs are connected to. You might need to look on the datasheet to see which pin is connected to. In my case, it's 33. When testing, I noticed a few of the pins were restricted, so you couldn't use them as your LED pin. I think 32 was an example. Please check the guidance on the WLED website to see which one's right. The project itself turns the ESP32 into a self-hosted access point on your network. So if you add it to your Wi-Fi network, it will host a website that you can navigate to via your browser. I'm using it in AP mode, which means it's hosting its own Wi-Fi network itself rather than being part of my Wi-Fi network. And when I connect to the device, it brings up a control center, so I can change the brightness of the LEDs, I can pick the color, I can run pre-set patterns on it, which all looks really good. But I wanted to do something slightly more than that. Built into the project is support for different methods of sending data to it across the network. I've chosen to use the UDP method. So this is the specific format that the data is expected in on the board. I couldn't find anywhere online. They have quite a few examples online, but I was looking for kind of the simplest one to get started with. So I've written some Python code here, which I'm going to go down through to see how you can do your own. So this is the code which I've set up, which is the bare minimum. I kind of set it up to be the easiest starting point for someone to work on it. So we start with the imports. So we have sockets, which is for the network connection, and we have time and sleep for the sleep function, which I've added just to keep the code simple. Obviously, there's a better way of doing it than what I've done here. So the first four things are setting up the settings. So the UDP has an IP address. In this case, the default IP address is 4321 with dots in between. This is the default IP address when you're in AP mode. So the device has the ability to host its own Wi-Fi network. So if you don't want to add it to your wider network and you just want to directly connect to the device, you can close your Wi-Fi browser, so turn off your Wi-Fi to the main Wi-Fi network you're on, and then connect via Wi-Fi directly to the device. Then this will work because then you're connecting to it and you can access it. If you do add it to your main network, IP address will likely change. You can then look it up and then put it in here. I'm using the default port. I don't think this will change if you add it to the Wi-Fi network or you just run it in AP mode. So that's the default port there, so 65506. Then it's the number of LEDs in your string. So this is how many LEDs are connected to the microcontroller. I think, if I remember correctly, you can have 300 to 400 maximum LEDs within this format before you run into memory errors. But I've got less than 100 LEDs in the project, and you probably find you run into power issues and data integrity issues if you run a string longer than 100 before you reach the 300-400 that this network protocol allows. It then creates the LED array. So The way that this protocol enables it is it's a big array of the RGB values. So basically what you're adding to is an array of, say, if I had 100 LEDs, it'd be 300 values. So you'd have an R, a G and a B value, and then it would start again at the next pixel with an R value. Then we have the stuff on the sending. So I'm using the TPM 2.0 protocol for this. So we have basically the defined thing of how they want the data. So this is how they want the packets. You're unlikely needing to change this. I've written it in Python initially. People have written it in C, or if they've written it in Rust, but I've written it in Python here just because I'm familiar with Python. Didn't see a Python example somewhere, so I thought I'd create my own. Then we have the LED controls. So using the starting process, there is no way of indexing where the LEDs are. So there is no built-in index method. It's a string of just RGB values. It doesn't have an index in that string. So to work out the index, I've written a little bit of code here that basically identifies the first value of the index, which is the R value. So LED I equals R, and then the second value after the R is G, and the third is B. So that way you can index it based on the red values. So every third value is the index, and then it can work out what to do. This enables the code which I've written here. So this, if you're familiar with setting up, doing any LED control with the Arduinos, this will look familiar with the NeoPixel library. So you have the index and then the RGB values. So I is the index, and then R and G and B are the red, green and blue values. So I've got 3 or 4 loops here. It loops round for all the LEDs, so it goes through all the LEDs in the collection and then sets all of them in the array to red. And then it sends this data to the strip. So it's writing all of the data first and then sending it all as one long string, so they all turn on at the same time. Then I have a sleep function here. Obviously there's a better way of writing this, but for code simplicity I've left it in here. I've then repeated the code for green and blue and then turning off the data itself. Obviously you can delete this and then rewrite your own code to do stuff, but basically the key parts are set LED and then tell the LED color what you want it to be, and then send that data to the strip. So how does this work with MIDI? So here on this line of set of code, I've basically expanded on that project, and I've imported MIDI, which is the MIDI control library. I initially wanted to use the new Microsoft library API for MIDI control, but that's not currently in the available yet. It's still being developed. So I started writing this in C# and then moved over to Python when I realized it wasn't ready. MIDI messages being received by the program fall into 2 main categories. We have note messages, so we have a note on message which has the channel, the note, the velocity and the time factor, and then when you release the note on the MIDI controller there's a note off one. So you have an on-off thing, so you can program effects to trigger on, note on, which I have done for my programs. So the other type of data that MIDI provides is change control data. This comes when you change the knobs on your MIDI controller. So if you turn the knob, it changes and you get a control value. So here we can see that we're getting the change control, which is the keyword we were looking for, the channel, which is 0, and then the control number. So the control number is the knob that you turned. So each of the knobs and dials on your MIDI controller has its own control number. These are hard coded, I think, to the controller. So when you set up a program, you can say control 49, I want to do a certain thing. And then you have the value. These values run from 0 all the way up to 127. In my programs, I've remapped those values to 255, so they're 8-bit mapped values instead of the range they are at the moment, which is more in line with what LEDs are. Using these two different types of values, I've asked the software to look for them when the messages come in and then trigger certain effects. With the note on message, I've had it set so it triggers the effect. I've set up two different effects in my two different programs. I put both the codes in the Github. I have a chaser effect where the LED starts at the bottom of the LED string, so effectively pixel 0 or pixel 1, and then runs all the way to the end of the string. This is triggered when it receives a note on. It uses the velocity of that note on message to affect how fast it travels down the string of LEDs. The other type of code we've got in my GitHub is to do with how long the notes are turned on for. So I use the note on message, and then as the note on is on, the time passes after that point and it increases the brightness of the LEDs and makes it spread to more LEDs. When you release it, then the LEDs start to fade. Obviously you can use these controls, these incoming messages, to do whatever you wanted within your code. So if you wanted a specific effect you wanted, or you wanted to trigger just certain LEDs, you can do that. In an early version of the code, I have the note on number, which reflects to the key you're pressing, trigger a certain LED in the string. So you can say, I want have a rope of LEDs down the back of my keyboard, and when I press the note on the keyboard, the LED behind it turns on. That's feasible within this system. During my testing, it doesn't seem to have affected the MIDI going into FL Studio. So if I open up FL Studio, on one screen you can see the MIDI coming in, so you can see the notes appearing, and on the FL Studio it's receiving the input. So it doesn't appear to be affecting the input of the MIDI data. So both of them are receiving it at the same time.